omega AB. What will be omega AB now? This is d alpha by dt. Okay, so just divide this d alpha by dt, we will get what? Del v by del x. Sorry. Similarly, omega AD. This will be d beta by dt. Okay, so this d beta by dt will be equal to del u by del y. Getting this now? Okay, now this will be with negative sign because this is moving in opposite direction. If we are taking anti-clockwise as positive, so this will be negative, so this will be minus del u by del y. Okay, now the average angular velocity. So what will be now the average angular velocity? Omega z. This will be the average of these two, omega AB and omega AD. Okay, so the average of omega, so this will be half of omega AB plus omega AD. Okay, so just put the values. So here we have omega AB as del v by del x, omega AD is minus del u by del y. So this will be equal to 1 by 2 del v by del x minus del u by del y. Getting this? Okay, so from here this omega z will be equal to half del v by del x minus del u by del y. This is omega z. Clear or not? Okay, similarly we can determine omega x and omega y as well. Okay, so from here this omega x will be equal to half of del w by del y minus del v by del z, and omega y will be equal to half of del u by del z minus del w by del x. Clear or not? Okay, so this is how we can determine the omega x, omega y and omega z. Okay, now for irrotational flow, this rotational component and the omega x, omega y and omega z will be equal to 0 for a rotational flow. If omega x is equal to 0, then you can say del w by del y is equal to del v by del z. If omega y is equal to 0, then del u by del z will be equal to del w by del x, and if omega z is equal to 0, then del v by del x will be equal to del u by del y. Okay, so these are the conditions for irrotational flow. For irrotational flow, del w by del y is equal to del v by del z, del u by del z is equal to del w by del x, and del v by del x is equal to del u by del y. Okay, now in case of, that means in case of irrotational flow, the cross velocity gradients are equal. Cross velocity gradient means the change in velocity of u with respect to z will be equal to change in velocity in direction of z with respect to x. I think this is called as a cross velocity gradient. So in case of irrotational flow, the cross velocity gradients are equal. Okay, now you can note few things. The very first thing, the rotation of the fluid element can only be produced by shear stresses caused by viscous action. As I have told you, that distortion is because of the shear action, because when the velocity is different in the u velocity is different in y axis and v is different in x axis. Okay, so this is because of the shear stress only caused by the viscous action. Second note, the shear stress is absent in ideal fluid, so the ideal fluid is regarded as irrotational except for flow along curved path. Okay, the shear stress is absent in ideal fluid, so the flow of ideal fluid is always irrotational. Next, within boundary layer, the viscous effect is of considerable importance, resulting in high shear stresses causing the flow to be rotational. Okay, as we will see this thing in boundary layer, you can see the lecture. So there the viscous effect is of very much importance. Okay, therefore there is very high shear stress which cause the flow to be rotational. In boundary layer, the flow is generally rotational. Okay, next, in case of irrotational flow, as I told you, cross velocity gradients are numerically equal. Getting this or not? Okay. Okay, now what will be the rate of shear strain in this particular case? Okay, so in this case, what will be rate of shear strain? What will be shear strain? Total shear strain will be equal to d alpha plus d beta. And when I say plus, I mean we have to add the magnitude of d alpha and d beta. The negative sign will not be considered. So this will be total strain. Total rate of shear strain will be equal to d alpha by dt plus d beta by dt. Okay, and what is this d alpha by dt and d beta by dt? D alpha by dt is del v by del x, d beta by dt is del v del u by del y. Okay, so this will be equal to del v by del x plus del u by del y. This is strain, rate of shear strain, epsilon xy. Okay, similarly epsilon yz you can calculate. So this will be equal to del w by del y plus del v by del z. Getting this on rate of shear strain. Now I will tell you one interesting thing here. We have discussed about Newton's law of viscosity, and that we have discussed in 2D plane, and it was the shear stress there was tau is equal to mu into du by dy, where this du by dy was the rate of shear strain. Here we considered the 2D case only. Now what will be the Newton's law of viscosity in 3D plane? In 3D plane means like this. Okay, here shear stresses will act. Here it will be tau xy, tau xz. Okay, how to denote this I have already told you in the strength of material if you have watched the lectures. If I am drawing this, the first subscript x represents the perpendicular direction. Okay, so perpendicular to this plane is the x-axis, so this will be x, and second subscript represents the same plane in the direction in which we are indicating the arrow. So this is tau xy, this is tau xz. Okay, similarly we have here as this will be tau yx, this will be tau yz, here this will be tau zx, and this will be tau zy. Getting this now? Okay, now what will be Newton's law of viscosity for 3D flow? So for 3D flow, Newton's law of viscosity says this tau xy, which is equal to tau yx, which will be equal to mu into rate of shear strain. What is rate of shear strain here? Tau xy is del u by del y, del v by del x plus del u by del y. Getting this now? Okay, similarly tau yz will be equal to mu into del w by del y plus del v by del z. Getting this? Okay, so in some question you may find this for 3D flow, the Newton's law of viscosity. Okay, so next topic is velocity potential or potential function, and this velocity potential is denoted by phi, and this phi is defined as minus of phi is equal to integration of vs ds, or you can say this phi, if I differentiate this I will get what? D phi is equal to minus vs ds. Okay, or you can say vs is equal to minus d phi by ds. Okay, so from this we can define this phi. Vs is equal to minus of d phi by ds. Okay, so how can we define this phi? What is this phi? The velocity potential is actually a scalar quantity whose negative derivative with respect to any direction gives velocity in that direction. I will define again. Velocity potential is a scalar quantity which is dependent upon space and time. Its negative derivative with respect to any direction gives velocity in that direction. The negative derivative with respect to any direction gives velocity in that direction. Okay, so if you want you can write the definition. Velocity potential is a scalar quantity dependent upon space and time whose negative derivative with respect to any direction gives velocity in that direction. Okay, now what does this mean? Now negative derivative in any direction gives velocity in that direction. That means u will be equal to minus of d phi by dx. Negative derivative with respect to x gives velocity in the direction of x, which is u. Similarly v is equal to minus of d phi by dy, and w is equal to minus of del phi by del z. Okay, now what does this negative sign indicate? This negative sign is indicating that the velocity potential is decreasing in the direction of flow. Negative sign indicates velocity potential is decreasing in direction of flow. Okay, that means for a possible flow the velocity potential must decrease in the direction of flow. Okay, now we know according to continuity equation del u by del x plus del v by del y plus del w by del z is equal to 0. Okay, now further what can we write? Del u by del x and u is equal to minus of del phi by del x. Okay, so this will be equal to what? Minus of del 2 phi by del x square minus del 2 phi by del y square minus del 2 phi by del z square is equal to 0, or you can say del 2 phi by del x square plus del 2 phi by del y square plus del 2 phi by del z square is equal to 0. Okay, this is Laplace equation. Okay, now omega z as we know is what? 1 by 2 del v by del x minus del u by del y. Okay, now further this can be written as, this will be 1 by 2 del v by del x, and v is equal to minus del phi by del y, u is equal to minus del phi by del x. Okay, so this will be equal to minus of del 2 phi by del x del y minus plus del 2 phi by again del x del y. Okay, and this will be equal to 0. That means omega z is equal to 0, and omega z is equal to 0, that means the flow is irrotational. Very important thing. Okay, that means if a velocity potential exists in a particular flow, that means that the flow is irrotational. Velocity potential exists in irrotational flow only. Okay, so you can write few notes here. The very first note, the existence of velocity potential in a flow field ensures that the flow is irrotational, as I told you. Second thing, irrotational flow is also called as the potential flow. Okay, and the velocity potential satisfy Laplace equation. Then the lines drawn in the flow field along with phi is constant is known as the equipotential lines. Okay, now what are these equipotential lines? If we are drawing the lines such that in the flow at all the points of these lines the velocity potential is constant. Okay, at all the points of the line the velocity potential is constant at all these lines. Suppose here it is phi 1, here it is phi 2, here it is phi 3. That means at all points the velocity potential here is phi 1, here is phi 2, and here is phi 3. Okay, so if the velocity potential is constant, a constant velocity potential line is drawn. Okay, these lines are known as equipotential lines. Okay, that means the velocity potential in those lines are constant. Next is the stream function. Now what is the stream function? This is denoted by psi, and this stream function is defined as the scalar function of space and time such that its partial derivative with respect to any direction gives velocity component at the right angle in counterclockwise direction. The partial derivative with respect to any direction gives velocity component at right angle. Now what does this mean? Okay, so suppose this is our axis, here we have x, here we have y. Okay, here velocity component here is u, here is v, here is minus u and minus v. Okay, now how can we define stream function? The derivative, partial derivative with respect to any direction. Suppose we are taking with respect to x direction. Okay, so the partial derivative with respect to x direction will give the velocity at right angle. Okay, velocity at right angle in counterclockwise direction. So if I am going in counterclockwise direction at right angle, I will get the velocity here. So this del psi by del x will be equal to v. Okay, partial derivative with respect to any direction gives velocity component at right angle. Similarly, del psi by del y. Okay, now if I am taking partial derivative with respect to this direction, this will give me this will give me the velocity component at right angle. That means at this. Okay, so this will give me minus of u. Getting this? The partial derivative with respect to any direction gives velocity component in right angle in counterclockwise direction. Okay, now for irrotational flow, as we know, omega z is equal to 0. Okay, and since omega z is equal to 0, so del v by del x should be equal to del u by del y. Okay, now in terms of psi, del v by del x, and v is del psi by del x, so this will be equal to del 2 psi by del x square should be equal to del u by del y, and u is equal to minus of del psi by del y minus of del 2 psi by del y square, or you can say del 2 psi by del x square plus del 2 psi by del y square. This should be equal to 0. Okay, this is the condition for irrotational flow. This is for irrotational flow. Getting this? Okay, now if this equation does not, if this equation is satisfied, the flow is irrotational, and if this equation is not satisfied, the flow is rotational. That means if the stream function is given and if you have to determine whether the flow is irrotational and rotational, just check with this equation. If this is satisfying, then the flow is irrotational. Okay, now what will be the stream lines? We have seen the equipotential lines, similarly where the velocity potential was constant. Similarly, the lines in which at every point the stream function is constant. For the constant stream function, if we are drawing the lines, suppose like this, so these are the lines of constant stream function. That means psi is constant here, and such lines are called as the stream lines. Getting this now? Okay, now there is one importance of this streamline, and that importance is if I take the difference between two streamlines, that means psi 1 minus psi 2, very important thing. This will give me the discharge between these two streamlines. The difference between two stream functions, psi 1 minus psi 2, will give me the discharge between those two stream lines. Very important note. Okay, so now we will solve few questions. Which of the following represents irrotational flow? Irrotational flow. So I told you the condition for irrotational flow: del 2 psi by del x square plus del 2 psi by del y square. This should be equal to 0. Okay, so just check all these conditions. So very first condition says psi is equal to 2xy. Okay, now from this expression itself, we can predict that this will be irrotational flow. Why? Because this is just the first degree of x and y, and the second degree, if I differentiate it up to 2 degree, it would be 0. That means del 2 psi by del x, here del 2 psi by del psi by del x will be equal to 2y, del psi by del y will be equal to 2x. Okay, del 2 psi by del x square is equal to 0, del 2 psi by del y square is again equal to 0. Therefore, this is an irrotational flow. Getting this? Very simple to determine. Clear or not? Okay, next, psi is equal to x square y minus 2y square. Okay, now del psi by del x is equal to 2xy, del psi by del y is equal to x square minus 4x. Okay, now del 2 psi by del x square plus del 2 psi by del y square. Okay, so this will be equal to what? Just differentiate this with respect to x once again, 2y, and differentiate this with respect to y plus 0. So this will be 2y, which is not equal to 0. So this is not an irrotational flow. This is an irrotational flow. Similarly, third condition, psi is equal to x cube y minus 3 x square y square. Again, from the expression itself, it is clear. Del 2 psi by del x square plus del 2 psi by del y square. Okay, so this will be what? If I take del psi by del x, it will be 3x square y minus 6. Okay, here del psi by del x is equal to 3x square y minus 6x y square. Del psi by del y is equal to x cube minus 6x square y. Okay, now if I take del 2 psi by del x square plus del 2 psi by del y square, obviously from the expression itself it is clear that this will not be equal to 0. Okay, so this is again not an irrotational flow. Okay, now last case, psi is equal to x square minus y square. Here del psi by del x is equal to 2x, del 2 psi by del x square is equal to 2, del psi by del y is equal to minus 2y, and del 2 psi by del y square is equal to minus 2. Therefore, del 2 psi by del x square plus del 2 psi by del y square is equal to 2 minus 2, which is equal to 0. Okay, so this is a irrotational flow. Okay, so this is how we can easily check whether the flow is rotational or irrotational flow if the stream function is given. Okay, next question, give the condition for irrotational flow. Okay, so here v is given as ax minus byi plus cx minus dyj. Okay, so from here we can say this u will be equal to ax minus by and v will be equal to cx minus dy. Okay, now for irrotational flow, del u by del y should be equal to del v by del x, as we have seen. Okay, for a rotational flow, del u by del y should be equal to del v by del x. Okay, now what will be del u by del y here? So this del u by del y will be equal to b, and del v by del x is equal to c. Sorry, this will be minus b, this will be c. Okay, so this is the condition, b is equal to minus c. This is the condition for an irrotational flow. Getting this? Okay, next question. Psi is equal to 2xy. What is the velocity at 1 1? Okay, so velocity we have to determine, and velocity how can we determine? V is equal to what? Under root of u square plus v square. So if I determine u and v component, I can be easily able to determine velocity. And we know what u is equal to what? Minus del psi by del y. Okay, so this will be minus of del psi by del y minus of 2x. Okay, v is equal to minus of, sorry, v is equal to plus of del psi by del x, so this will be 2y. Okay, now at 1 1 1 and minus 1, this u will be equal to minus 2. Here also at 1 and minus 1, this v is equal to 2. Getting this? Sorry, minus 2. Okay, so this v is equal to under root of 2 square or minus 2 square plus 2 square. So this will be equal to 2 root 2. Answer. Getting this? Okay, next question. Psi is equal to x square minus y square. What is the discharge between two streamlines passing through 2 1 and 2 2? Okay, so we have two streamlines, one is passing through 2 1 and second is passing through 2 2. We have to determine discharge. So as I told you, discharge q is equal to what? Psi 1 minus psi 2. Okay, here psi 1 will be equal to x square minus y square. At 2 1, psi 1 will be equal to 4 minus 1, which is equal to 3. Similarly, psi 2 is equal to, at this is x square minus y square, at 2 2, psi 2 will be equal to 2 square minus 2 square, which is equal to 0. Okay, so this q is equal to psi 1 minus psi 2, which is equal to 3 minus 0, which is 3 units. That's it. Okay, very simple questions. Clear or not? Okay, next topic is the flow net. Okay, now what is flow net? We have seen in the equipotential lines, we have seen the stream lines, and both are perpendicular, as I told you. Okay, so if we see the grid which is formed by the equipotential lines and stream lines, that grid is nothing but flow net. Okay, so the equipotential lines were like this, phi 1, phi 2 and phi 3. Okay, and the stream lines were like this, psi 1, psi 2 and psi 3. Okay, so if the grid is formed between the equipotential lines and the stream lines, that grid is nothing but the flow net. Getting this on? Okay, we will see certain properties of this flow net. You can note it down. The very first thing, the potential function is defined for irrotational flow only, hence it has to compulsorily satisfy Laplace equation. The potential function, as I told you, is defined for irrotational flow only. Okay, so it has to satisfy the Laplace equation. That means del 2 phi by del x square plus del 2 phi by del y square plus del 2 phi by del z square should be equal to 0. Next note, stream function may not only be defined for irrotational flow but also for the rotational flow. Okay, The potential function is defined only for irrotational flow, but the stream function is defined for irrotational flow, and it can also be defined for the rotational flow as well. Okay. Third thing, the product of slopes of streamline and equipotential line at the point of intersection. The product of slope m1 and m2, this will be equal to -1. Why -1? Because these are perpendicular, as I told you. Okay, so the product of a slope, as we know, will be equal to -1. Okay. Next, the streamlines and equipotential lines are orthogonal to each other, as I told you, except at the stagnation point they are orthogonal, that means they are perpendicular to each other. Okay. Next, if the distance between the streamlines at some small region of the flow is delta n and distance between equipotential lines is delta s, then for the flow net delta s is equal to delta n. That means if suppose the distance between the streamlines is delta n and distance between streamlines is delta n and distance between the potential lines is delta s, then del n will be equal to del s. Okay, so these are all important points for this, or you can say del phi will be equal to del of psi. Getting this? Okay. Next topic is the vortex flow. Okay. Now, what is a vortex flow? When the whole mass of fluid is rotating about an axis, then we can say it is a vortex flow. I will tell you few characteristics of this vortex flow. The very first thing, the whole fluid mass must rotate about an axis. First thing. Second thing, the streamlines should be curved. The streamline should be curved. And third thing, the radial component of the velocity should be 0. Okay, that means there will be only tangential component, the radial component in the direction of radius, the velocity should be 0. Now, this vortex flow can be either a free vortex or it can be a forced vortex. Okay. Now, what is this free and forced vortex? Now, if the fluid is rotating such that there is no rotation about its own mass center, that means for irrotational flow. Okay, so the vortex formed is known as free vortex. Okay, if there is no rotation about its own mass center, then it is called as the free vortex, which is formed in irrotational flow. And if there is rotation, if the flow is such that there is rotation about its own mass center, then it is called as the forced vortex. Okay, so I will tell you few differences between this free vortex and forced vortex, and with that this thing will be very clear to you. Okay, so for this free vortex, we will draw the column, and this is forced vortex. Okay, so very first thing, there is no external torque here. Okay, there is no external torque in this free vortex, and there is external torque in the forced vortex. Okay, the example you can see, example of the free vortex is the whirlpool of river. External torque we are not applying, the vortex is produced naturally, like whirlpool of river. Okay, or if you have seen the flow through the bottom of container. Or around circular bands, flow around circular bands. Okay, these all are the example of free vortex. Okay, now forced vortex means there is an external torque, obviously. For example, the flow through the runner of blade. Okay, or you can say the flow through the pipe, through pumps, impeller pumps. Okay, all these examples are that of forced vortex. That means the external force is applied in order to produce the vortex, that is known as forced vortex, and free vortex is produced naturally. Second difference, as I told you, this is for irrotational flow. That means the fluid is not rotating about its own mass center, and this is for rotational flow. Getting this or not? Okay. Now next thing, for this free vortex, okay, the streamlines are concentric circles like this. Okay, streamlines are concentric circles, and if I am taking a small element here, PQRS, the velocity here is V. Okay, the velocity is changing here, and this here the velocity will be V plus dV. Getting this? This distance is dr, and there is no radial direction velocity, as I told you. Okay, so radial velocity is 0. This is radius r. Now circulation is equal to, now as I told you, what will be the circulation here for this element PQRS if I want to calculate circulation. So this will be V plus dV, summation of product of velocity component and the elemental length. So V plus dV into the elemental length is nothing but r plus dr into d theta. Okay, into r plus dr into d theta. Clear? Plus, now for this PQ, velocity is 0, since the velocity is 0 in radial direction, plus 0 minus, okay, opposite sign, minus V into this distance of this PS arc, which is r into d theta, V r d theta plus 0 for SR. Okay, now neglecting higher order terms, we will get what? D circulation is equal to V dr plus r dV into d theta. Clear? Okay, this is nothing but the circulation. Now vorticity, what will be vorticity now? Zeta is equal to d circulation divided by area. Okay, so this will be V dr plus r dV into d theta divided by area. Okay, now what will be this area? Okay, so this is nothing but r into d theta. This is r into d theta into dr. Okay, so this will be r d theta into dr. So from here this will be V by r plus dV by dr. Getting this? This is nothing but vorticity. Now this free vortex, as I told you, is for irrotational flow, and for irrotational flow this vorticity should be equal to 0. That means for irrotational flow, zeta is equal to 0. That means V by r plus dV by dr should be equal to 0, or you can say V dr plus r dV should be equal to 0. Now dividing by V r, we will get what? Divide this by V into r, V will get cancelled out, we will get what? dr by r plus dV by V. This should be equal to 0. V dividing this by V into r. Okay, integrating this, we will get what? Ln of r plus ln of V. This should be equal to constant, or you can say V into r is equal to constant, or you can say V is equal to C by r. Very important conclusion. For free vortex, V is equal to C by r. That means V is inversely proportional to r. That means as the radius increases, the velocity will decrease. Okay, therefore for this free vortex, as I told you, so here suppose the angular velocity here is omega 1, here it is omega 2. Okay, so the very first thing, let's compare it with forced vortex at the same time. Okay, so the very first thing in forced in free vortex, because there is no external torque, therefore this omega 1 will not be equal to omega 2. Okay, there will be the difference in angular velocity, then only there can be vortex, because there is no external torque and no external force. Now the question arises, which will be greater? So as I told you, V is inversely proportional to R. Okay, that means velocity decreases as the radius increases, or angular velocity decreases as the radius increases. That means at higher radius, that means this omega 1 will be less than omega 2, or omega 2 should be greater than omega 1. Very important conclusion. Getting this? Because V is inversely proportional to R. Okay, and because there is no external torque, therefore there has to be some difference in angular velocity, then only it will produce vortex. Now on the other hand, for rotational flow, for a forced vortex, because there is an external torque, so because of external torque, here omega 1 will be omega 2, which will be equal to omega. This will be same. Getting this not? Okay, and we know what omega is equal to V theta by R, and this omega is a constant. Okay, and this V theta is 0 at origin and increases as R increases. Okay, so this V theta will be 0 at origin, but this omega has to be constant, so as R increases, this V theta also increases. Getting this now? Okay, so this is the difference, main difference between free vortex and forced vortex. Okay, now one more difference, that because there is difference in angular velocity, so obviously it will produce the shear stress because of the relative velocity. So here the shear stress is present because omega is variable. Okay, and here no shear stress. Getting this one? Okay, so this is how we can define this free vortex and forced vortex. The very first thing, there is no external torque in the free vortex, and there is external torque in the forced vortex. The examples as I gave you, all the vortex which are naturally produced, like for example the whirlpool of the river, the flow through the bottom of the container or through the bends, wherever the vortex is produced naturally, that comes under free vortex. Okay, and the forced vortex which is produced forcefully, for example in turbines, in pumps, the impellers of the pump. Okay, so those are called as forced vortex. These are for irrotational flow, these are for rotational flow, as I told you. Now here one more thing, that because no external torque is there and the vortex is produced because of the difference of angular velocities, so the omega 1 is not equal to omega 2, and as the radius is increasing, omega is decreasing, so omega 2 here is greater than omega 1. Okay, here omega 1 will be equal to omega 2. The velocities are same, since the angular velocities are same since the vortex is produced because of the external torque. Getting this? And because of this difference in velocity, the shear stress is present here and shear stress is not present in this particular case. Clear or not?